Yes, so everyone, welcome to my talk on the applications of FTIR or Fourier transform infrared spectroscopy for regolith mineral exploration. Yeah, my name's Harrison Keeble, and I'm currently a geoscientist at the Geological Survey of Victoria. And as Owen said, I'm working on the banded mines framework. Specifically, my focus is sort of spectral science on how we can sort of further that field in Victoria. So this talk is put together from some of the research I did during my honours last year at UTAS. And for that, I'd like to acknowledge my supervisors, Dave Cook, Lejun Zhang. It was actually Thomas Roadman as my other supervisor in chemistry, as well as Ned Howard from Evolution Mining, who was the sponsor of my company of the honours project from Evolution Mining. So here's a bit of an overview of the talk for today. I've separated it into two parts. The first part is looking at the characterization of the regolith profile at the mine site, Keeble Gold Mine, and the E41 deposit, which was my focus. So go over a bit of a background geology on the site, and then go through the regolith profile, sort of some of the techniques and the interpretations that I made throughout my honours year. Then the second part of my presentation will focus on the other part of my honours, which was looking at predicting geochemistry and some models for that purely from spectral data and particularly FTIR spectral data. And finally, I'll conclude with a few applications and future work for the FTIR. So to start with the regolith profile of E41. So E41, which is located at the Keeble Gold Mine, is operated by Evolution Mining. It's in central New South Wales. You can see it just here. It's part of the Gin Narromine volcanic belt within the Macquarie Arc and is a low sulfidation epithermal gold deposit. On the right, you can see a bit of a figure site plan of the Keeble Gold Mine. You see E42, the main deposit, in the open pit for the mine. Just to the south of it is E41, sort of half covered down here by the ephemeral Lake Keeble. So this deposit has no outcrop or anything, and all my samples are purely from drill core. The gold mineralization at E41 is quartz pyrite, calcite, adularia, and carbonate base metal sulfide veins, and there's also a significant supergene gold zone in the regolith, which was the particular focus of my honours project. So here you can see a cross-section of E41. This was created by Wojtek Sikowski for his 2010 PhD and subsequent papers. He focused on the protolith, particularly on the veins, mineralization, and alterations. And he, for the most part, left the regolith alone, which I've highlighted here in red, although he did identify several high-grade gold zones from the assay from the drill core throughout his work, which is going to be the focus of my project, and was sort of the idea from evolution is to identify where these grade zones are and sort of what's the mineralogy associated and various other things about the regolith. So onto the structure of the regolith. So on the left here, you can see a generalized log that I've created across the whole deposit, as well as the different units that I've defined and their general thicknesses. So start with the protolith. So across the deposit, it varies between altered mudstones, monzonites, and diorite across the deposit in the two separate sides of it. From here, from this altered protolith, transitions into a sap rock, which is about 10 to 30 meters, varying across the deposit. And in the saprolite portion of the residual regolith, there is the lower frogginous saprolite, which is variable between 10 and 75 meters. This sort of thicker portions are in the eastern portion of the deposit. Then in the upper part of the saprolite, I defined it as upper kaolinic saprolite, which again, a bit variable, 10 to 25 meters. And finally, the residual regolith is capped by a thin silcrete layer. Above the residual regolith is transported material, which in this case is the custrine sediments from the ephemeral Lake Keeble, as I mentioned before. And this overlays the whole deposit, again, with a pretty variable thickness between 3 and 10 meters. On the right, you can see some images from one of the drill holes of chip trays that I collected during my logging campaign. So firstly, we have those transported lacustrine sediments. They're a mixed origin. The color varies quite widely across the deposit. It's very, again, because of the lake, it's very hard to determine the exact origin of these sediments and their strict mineralogy. So I've just classed them generally as lacustrine sediments. You can identify between the lacustrine sediments and the residual regolith by this silcrete layer, which is creamy white in appearance, pretty typically angular to subangular quartz grains in a fine quartz matrix, and is often dusted by this hematitic dusting quite pervasively across the deposit. For the saprolite, we first have the upper kaolinic saprolite, getting its name from the greater proportion of kaolinite in comparison to the rest of the regolith. It's also creamy white, but also has this pervasive sort of orange yellow color that's coming again from the iron oxides in the regolith. Then going down deeper, we have the lower frogninous saprolite, this getting its name from a very high proportion of iron oxides in comparison to the saprolite, the upper saprolite. You can see some of those here, this sort of dark material here and here, quite throughout the this section. There's also a good amount of manganese oxides that are discovered while logging, which is pretty cool. And finally, for the residual regolith, we have the sap rock, which is marked by rock chips with a coherent rock texture. And then this would transition more into sort of coherent or more coherent rock as you transition back into the altered protolith. So initially, the goal for this project with the regolith was to identify gold and the associated mineralogy. So the first thing we looked at was the iron oxides, the oxides in the regolith. So during this, I did this through reflected light microscopy, as well as a good amount of work on the SEM, which collected some of these images. So there were 4 key textures or most common textures that were found throughout the deposit. Which you can see here, I've labeled them A through D, and you can see where they're located on the log and the depths. So the first texture, which is the most uncommon, was the least oxidized, which was the partially oxidized pyrite. You can see that here with some very weathered pyrite with a rim of goethite around it. This is found in the lower sap rock where the extent of oxidation isn't as great. Then we have the most common texture, the cellular boxwork iron oxides. This is common right throughout the profile, as I mentioned. And then the 2 textures with the greatest extent of oxidation were the coliform banded goethite and hematite, as well as the coliform banding with botryoidal goethite, which made for some pretty spectacular pictures under SEM. So initially, the gold we were looking for was as visible gold species. So we hope to be able to see that pretty clearly in the reflected light, but particularly in the SEM. Unfortunately, considering the high grade, we didn't really see much at all. We can sort of see some very fine specks of electrum here in this case here, but it didn't represent the grade from the assay. So to combat that, we took some L8 ICP-MS multi-element maps with particular focus on the iron oxide grains, because that was the theory of to where the gold was located. And you can see some of those maps here onto the right. You can see it's pretty high-grade gold right throughout these samples. What we discovered was the majority of the gold was located as lattice-bound gold within the oxides, particularly goethite. You can see here the gold is associated with certain zones of growth within the goethite, which is mirrored here in the copper and cobalt maps. You can see the copper matches pretty much exactly with the gold locations, and the cobalt is revealing even more growth zones. But you can also see there's a significant amount of gold throughout the rest of the gold grain without following some of these other zones. So that's a very interesting formation. I mentioned that there was visible gold, which you can see here in this image, a few examples, but this analysis showed that visible gold was also present with lattice-bound gold, which you can see here quite a lot throughout this whole image. I'll note here that all the visible gold and the analysis that we took were from the sap rock, because to analyze in laser, we need a laser mount, which just because of the condition of the core that was analyzed and the nature of the material in the saprolite, we weren't able to make mounts to analyze them. However, I did do some powder mounts and analyzed the saprolite. I didn't identify any visible gold just because of how fine the material was. And I didn't get a chance to analyze any of these grains on the laser, but I would be highly confident that there would be this lattice-bound gold in the grains in the saprolite. However, due to the scope of the honors, I didn't get a chance to do that. Some of the highest grade areas are actually in the lower frogginous saprolite. Now, some of you may have noticed that I've been using the mineral names for the different oxides in some of these samples. And you'd also see that it's quite hard to distinguish between the two in these images, particularly reflected light. And then even in the SEM, it's quite hard to distinguish. To introduce how we came to naming these and how we could identify them, I just want to introduce infrared spectroscopy, which was sort of the main focus of my honours project. Just for anyone not aware, here we have the electromagnetic spectrum. See these rainbow colours here is the visible light that we can see with the human eye. And beyond that, we have infrared light, which is its own, which is separated into their own subcategories. So within geology, we can identify different minerals by zapping them with a little bit of infrared light, and then what comes back off we measure, and what comes back we can measure uniquely for every single mineral and material on Earth. Commonly within geology, you'll see that it's used like this as a hand analyzing tool. This is Terrascope Halo analyzing this outcrop here. That's also used well beyond geology, particularly here in chemistry. They're looking at the composition of a tire. So each mineral comes back with this spectrum when analyzed, and there are certain parts of it that are unique to that mineral, so you can distinguish them. And this is how we managed to determine between the different oxide species, because they have a unique spectrum. Here you can see the difference between alunite and kaolinite, as the spectrum are quite different. The blue here, the kaolinite, and the red, the alunite. This led us to use special infrared technique, Raman spectroscopy. Doesn't really matter what that is exactly, but it allowed us to create these maps. So some of you may be familiar with AMIX or other mineral identification, automatic mineral identification techniques used with the SEM. It also creates these maps, but with the infrared, we can take some of our samples and analyze them with the Raman and create these maps, which can then identify what minerals are present and then color them based on whatever colors we would like. So in the blue here, you can see we have hematite, in the red, goethite, and in the purple, sort of magenta color, you can see hematite and goethite mixture. This was really vital in the initial stages of the work to identify and try to figure out exactly what minerals particularly were associated with the gold. You can see here, visible gold grain. So I really want to know what this gold grain was within. So a really interesting and important discovery when we did this Raman analysis was the presence of jarosite in with the goethite and hematite. The presence of jarosite with these meant that we could redefine the oxides as limonites, which I'm sure many of you are aware of what that means, but essentially it's a mixture between goethite, hematite, and jarosite. And you can see here, in hindsight, you can see the different colors and the different minerals that they're associated to, which was a really good guide for, particularly for targeting other analysis further down the track in the project. Now on to sort of the main focus of my honours project and this talk, which was on the predictive capacity of Fourier transform infrared spectroscopy, or it's more commonly termed as the acronym FTIR. With the main question posed from this being whether it's possible to predict spectral data, to predict regolith geochemistry purely from spectral data. And the short answer is yes, it's very possible. We did that with two different techniques. So we first analyzed with the FTIR, which measures the infrared spectrum in the SWIR, and then the FTIR, which measures the spectrum in, it's all combined, the SWIR, short infrared, middle infrared, thermal infrared, and far infrared. The sampling for this followed as collecting diamond drill core pulp from the core that I analyzed during my field campaign. I then took those pulp bags, split them into these little vials, which I then analyzed on the FTNIR initially, and I collected spectrum from that. Then I split them further and then analyzed with the FTIR device. which we then collected spectrum from again. And then finally, we would take that spectrum and compare it with a partial least squares regression to known assay data for each of these samples to see how well the spectra could predict the regolith geochemistry. So here's some of the results. You know, there's a lot going on the screen, but I'll walk you through it step by step. So initially, with these figures, we have the predicted concentration plotted against the absolute concentration. So the predicted is the algorithm used to predict the chemistry purely from the spectral data. And you can see those plotted as different colors and shapes based on depth of collection. This is all samples from within the regolith. To identify the success of the model and how well it's predicted the chemistry, we look at these three values here. So the R-squared value is essentially how well the data fits to a 1-to-1 line, so 1 to 100 or 1-to-1 being a perfect prediction, which you can see here, both of these are pretty exceptional, the highest that would ever actually gotten up to this point in the lab. And then the two more important values are the RMSE-CV value, which is up here, the root mean square error of cross-validation, which essentially is a measure in the error of prediction. So think error bars on each of the points for concentration. So in this case, 3,330. So there would be about 1,500 on either side, which you can see based on the scale we're working at, that's a very low error. And probably the more important or easy to understand one would be the relative percentage difference, or RPD, which is calculated by taking the standard deviation of the measured concentration and dividing it by the prediction error, or the RMSE-CV values. And this is looking at standard deviations away from the mean. So the higher the value, the better the prediction of the model. Typically, 2 is very good results. So you can see these being close to 6 and about 7.5. They're pretty exceptional models. We did models for pretty much a full suite of elements, but you can see some of the models are limited. They do have reasonable R-squares and RPD values. However, some of these models lacked sort of sample numbers. You can see here, majority of them had 0 concentration, and the ones, particularly in the sulfur, you can see most of them deeper down, which would probably remnant pyrite. There are a few ones up in the saprolite, but these again could be the very limited examples of jarosite present throughout the regolith. Again, you can see that with the phosphorus pretty bunched up, meaning that we have very limited samples. And again, the concentrations are quite low compared to the iron and aluminium we saw on the other slide. Here we have another 2 really good models. We've got a potassium prediction model and the calcium. And this is a really good example of looking at the concentration differences across the different portions of the regolith and really bunching up into categories of greater proportions. And this, you can also see the depletions when you go higher in the regolith profile. Again, both of these are pretty exceptional results, and the errors are quite low considering the samples that were analyzed. Yeah. So here's a few of the key takeaways from my project. So initially we saw some of those Raman maps. So this was really good for the really fine grained. You can see from the scale here, we're looking at very, very small scale samples, and we're able to distinguish between them quite clearly. The pixel size is very, very small, meaning that fine grain can be analyzed with high accuracy. It's particularly valuable because it's a non-destructive technique that has minimal sample preparation. So for these ones, we used laser mounts, putting them in essentially a modified reflected light microscope, finding the area we want to analyze and analyzing it. After a few minutes, it will produce one of these maps after checking with the spectral library that we have. And you could do this theoretically on core or any other sample that has a reasonably flat surface that you get a good response. And when you compare it to an SEM, AMIX, automatic mineral identification, it's far lower cost and far safer in a mineral analysis workflow. And then probably the best results I got out of the honours project was this partial least squares regression, predicting chemistry from spectral data. found it to be a possible alternative to whole rock assay in the future that's faster, cheaper, and safer. Again, non-destructive, so you'll keep these samples. And also the desktop setup. You probably saw from those images of the devices, they were just in a desktop, just a lab room. Doesn't have to be a clean room or anything, or have any other special setup. Nothing's under vacuum and nothing's cooled by liquid nitrogen, which is extremely valuable because you can have that in a wide range of locations. And Jim, thank you for coming to my talk. Short and sweet, but I hope you enjoyed.